Next, we look if the tensor notation for represent the state of stress inside of a continuum is consistent with Newton's second law. And so we've written Newton's second law for a continuum on the control volume. Now what I want you to think of is, let's say we have a control volume. This is our control volume, but now it's not a fixed control volume, but it is a material control volume. So the control volume depends on time. So we've derived Newton's second law for a continuum, and what we found is the following. The change of total momentum inside of a control volume is equal to the sum of the resultant forces, so the sum of all of the body forces plus all of the forces which are exerted by the continuum outside of our control volume onto our control volume. Note here that because we do not have a fixed control volume but a material control volume, I don't include here the flux of momentum through the interface, because there is none, because the volumetric flow rate through a material control volume is equal to 0. Now, the stress tensor really represents the state of stress or the forces exerted inside of the continuum at a local point. So it makes sense to shrink and to think about what happens when this control volume becomes infinitely small. So if we are making the dimension of this control volume become epsilon, and epsilon goes to 0, then you know that the volume is going to scale with epsilon cube, and the surface is going to scale with epsilon squared. So this integral here, eventually, when we go to 0, will tend to epsilon cubed. Same for this here, and only the surface integral will scale with epsilon squared. And when epsilon goes to 0, then these terms are going to go to 0 much faster. The two volume integral are going to go to 0 much faster than the surface integral, and therefore when we are really essentially at a single point, when epsilon has gone to 0, then we should have that the integral of the stress vector on an infinitely small control volume should be equal to 0. So let's see if our tensor notation is consistent with this description of the state of stress in a fluid. So what I'm going to do here is consider an infinitely small control volume, and I'm going to give it a special shape to make things easier. So I'm going to assume that my control volume is this thetahedron here, and I'm going to look at the stress vectors on each faces. And so on this face here of surface normal n, I may have the following stress vector imposed. So this represents again the forces exerted by the continuum which is on this side of the surface onto the continuum which is inside of my control volume on the other side of the surface. And then on each of the other three faces, I have other stress vector on the surface of normal minus x, on the surface of normal minus z, and on the last surface, the back surface here, which is the surface of normal minus y. And note that because we assume this control volume is really infinitely small, then I'm writing those stress vector at x and t, and here at the same x and at the same t, and here the same x and the same t, because I'm assuming essentially that is a little bit of the same everywhere, because it's an infinitely small control volume. And so now we are going to evaluate this integral. So for this we're going to integrate our stress vector over our surfaces. Now I'm going to call the area of the surface of normal n dA, and the area of the bit of the surface of normal minus x, I'm going to call that dAx, and same for the surface of normal minus z and minus y. And now I can write this equality here by adding my 4 terms on each surface. On the surface of normal n, the surface of normal x, plus the term on the surface integrated over the surface of normal minus y and minus c. And the sum of all of those 4 terms is equal to 0. Now we discussed before that this here, because of Newton's third law, this has to be equal to minus the stress vector on a surface of vector x, and this has to be equal to minus the stress vector on the surface of vector y, and this has to be equal to the stress vector on a surface the stress vector on a surface of normal z. So I can rewrite this expression here and write that 0 is equal to the stress vector on surface n. I'm omitting now the x and the t just for simplicity, minus the stress vector on the surface of vector x, dAx, and the 2 other terms corresponding to the 2 other surfaces. Okay, one thing which one can notice because of this tetrahedron geometry and the way I picked it, this surface here, dAx, is actually equal to dA times the dot product of x. I shouldn't put a dot here, so let me change that. It's equal to dA times the dot product between the vector x and the vector n. This is geometry. You can verify it if you want. You'll see that this is the case, and same for day and daz. So again, I can rewrite this. So the first term remains unchanged, minus here I can rewrite this as n dot x times the stress vector on a surface of normal x, and same for y and z. And now what you can see here is that if I put all of these terms, if I put all of this term here on the left hand side with a positive side, and I can simplify the dA, and I can factorize the dot product with n, and this yields n dot product of x tx. Note that this is the outer product between a vector and a vector, so this here is a matrix, plus the outer product between the unit vector y and the stress vector on the surface of normal y, and same for z. And this is equal to the stress vector on the surface of normal n. So note that this here is this term here correspond to a matrix plus a matrix plus a matrix. So really, this I just shown that we can write our stress vector t on a surface of normal n as n dotted a matrix, and this matrix is going to be our stress tensor. So yes, this mathematical description of stress as a matrix here is in agreement with Newton's second law, right? So yes.